I'm going to, first of all, give a call out to some of the folks who are very interested here in the US who are paying us at LBL to do these sort of studies, and that's primarily the US DOE Building America program, and also a couple of other branches of government here in the US, the Environmental Protection Agency and HUD. So I'm going to talk here about sensing for control, and a key thing is that the sensors themselves are relatively inexpensive here. We're talking about low-cost sensors, so it's an affordable option for controlling ventilation or filtration in the building. But they're often packaged into monitors that include power supplies, displays, some sort of internet connectivity, and usually cloud storage. And they're typically sensing things like temperature, humidity, particle matter, CO2, some of them VOCs. And they cost about $250, about 200 euros. The sensor inside them for particles is only a small fraction of that total. And these cheap sensors are based on light scattering devices. And it's important to note that they have a low limit on the size of particles they will detect of about 0.3 of a micrometer, and that will come in useful when we try and explain our results in a few minutes here. And the current focus is on particles, and what I'm going to talk about here is experiments where we compared these inexpensive monitors to reference and research-grade devices. And the things we're interested in is, can we detect an event that emits particles? And if we detect that event, do we get the magnitude of the number of particles or their mass correct? And what is the effect of different size distributions of particles? And what particle ranges do we get depending on the event that we use to generate the particles? And I suppose the bottom line here is this final question on this slide, which is, are any of these devices really good enough to make some decision about turning off a ventilation system or turning on and off some sort of filtration device so that we can actually use them for control? This is a picture of the laboratory where we evaluated the sensors. They're all side by side on a rack there. You can see off to the left is a very interesting source of particles, and that is a gas-fired cooktop. We filled this one with mixing fans to make sure all the particle concentrations were uniform. We have some computers there to do some data logging. The particle sources we're talking about here are all over the place. There are what we call general particles. There are standardized particles that are often used for determining how well air filters work. And there's something called Arizona road dust that some of you may be familiar with. There's also things like if you beat a carpet or a dust mop or run a humidifier. Then there are hot surfaces. In this case, we used a hairdryer and some electric burners. Some cleaning products that are used in homes, when combined with ozone, produce a lot of particles also, so we investigated that. There's particles from combustion, whether that's from smoking or candles or burning natural gas. And then we tried all sorts of different kinds of cooking events, some of which were done on the cooktop, things like stir frying and so on, others of which used an oven, and we did toasting and making pancakes. And all of these different sources of particles are going to produce not just different amounts of particles, but also different particle size distributions. The reference instruments that we used as our truth standard were a couple of devices. One was the thermoscientific TEOM, which is a tapered element oscillating mass balance. And there's a inset picture there of the tidal mass balance. When particles land on the tip of that device, it actually changes the oscillating frequency of it. And we used a Grimm Mini-RAS, which is an aerosol spectrometer, which gives us really good particle size distribution in 41 different bins of particle size. We also compared to a couple of devices that I would call research instruments, which are using similar principles to the inexpensive sensors. It's just they are much better made devices, and the calibrations are much more careful, and the devices are much more robust. And the thermoscientific PDR on the right there is what we used for some of our in-home measurements, because we wanted to also make sure there wasn't something quirky about our lab, and try and test a few of these instruments actually in somebody's home. So these are the 7 devices that we evaluated in our study, and this is just a summary that shows what they look like, and it's important to see that some of them have wonderful color displays, others don't have any display at all, and there's a few things in between. This lists the different things that they detect, and they all detect something slightly different, whether that's particles, temperature, humidity, or what have you. And also I listed here the recording time, because all of these devices are going to, in some way, they will log their recordings, and some log at shorter time periods than others. So what happens if we expose these low-cost monitors to something like dust from a dust mop, particles from candles, gas cooktop, turning on the oven, frying with oil? And here you just see a timeline of the various sensors, and the reference here is the dark thick line labeled GRM. That's our GRM. And you can see that our reference device basically detects every single one of these potential sources. But the low-cost monitors, some of them detect some of the events, but not all of them. In particular, the gas cooktop with the pots of hot water, with boiling water, and the oven were really not detected by these devices. And if you look at the different magnitudes of response in the particles, you'll see that some of these devices, like the purple air, pretty much is very close to the GRM. Other ones are reporting much, much lower concentrations. So the summary here is, in terms of event detection, some of these devices are better than others, and none of them are perfect. And in terms of the magnitude, in other words, do they tell you exactly what the concentration is? Again, some of them are better than others. And it depends a lot on the event. And in our terms here, what's happening is we are changing the particle size distribution depending on the event that we use. And so my next few slides are going to dig into this a little deeper. So I have a series of slides here, and they're all going to look the same. And what I want you to notice here is across the bottom we have labels for the different devices, and the vertical scale is the concentration of particles they are measuring. You can see that inset into that is a little graphic that shows the particle size distribution. And if we look at the dust mop and the 2 Arizona road dust samples, you see that the green area is shifted all the way to the right. So those are large particles. And for the humidifier, we see that it's more central in the particle size distribution. And so if we look at the differences here, we can see that for the large particles, the spec, which is on the far right, detects almost all these large particles well, but things like the purple air do not. But if we go to the bigger range of particles created by the humidifier, those results are kind of reversed. And we'll see this as a pattern here, in that some of these devices have been calibrated more for large particles, some more for a broader particle range. Here's a slide that is looking at the results for if you were burning things in the house, whether cigarettes, candles, or incense. And you can see that these have particle distributions that are shifted towards smaller particles. And the same pattern is repeated from the previous things, in that there are some devices that are good at sensing these smaller particles, such as the purple air, possibly the air visual node, but others like the Aware, the Air Quality Egg, and the Spec that really don't see these small particles. If we're looking at things like cooking, in this case we're frying things in oil, we see relatively broad particle distributions, but the pattern is roughly repeated. One thing I do want to point out is that sometimes you'll see no data, and I'll touch on that a little bit later. And this has to do with, were we able to retrieve data from the cloud or download data from these devices, and sometimes that doesn't work so smoothly. And well, here we can see again the particle size distribution is affecting what we see. With both the beans, we see that we're generating a bunch more larger particles again, and the spec is again seeing these particles, and other devices not so much, like the Air Quality Egg. So the summary of all these results, and I know I've gone through them quickly for you, and we can certainly revisit these if people have questions, is that clearly the different devices are calibrated differently depending on the particle size distribution. And one last slide on this is, if we look at events that emit small particles, less than 0.3 micrometers, I said at the top of this that the light scattering devices that are actually inside the sensors, we don't expect them to detect these very, very small particles. And here we have some typical cooking events that are not that unusual, things like burning toast, cooking pizza and pancakes, or just turning an oven on. but their particle distributions are very much in the smaller scale particles, and you can see that even our research grade instruments, the PDR, for example, does not see these small particles. The only device that saw the small particles was our reference device in this case, which is the GRIM or the GRM. So you can see that if we're looking for very small particles, these devices won't work. So let's look at some of the data from the in-home testing. And this is very similar to the chart I showed earlier. We only tested a subset so far of these devices indoors. And in this case, we're looking at burning some candles, emitting some chalk from a bag of chalk, and those of you who are indoor climbers will know what that is for. And you can see here that again, we see similar results from before, where not all these devices detect all the events. And again, the magnitudes are different depending on the individual event and its particle size distribution. Basically, if you light a candle, all these devices can detect that the candles were lit, but maybe not get the magnitude right. Chalk is interesting because it's almost certainly much larger particles than these devices have been calibrated for, with the exception of the speck, which, similar to the previous results, looks like it's been calibrated for much larger particles rather than smaller ones. Continuing these in-home tests, we cooked some French toast and we fried some bacon. And again, you can see this similar pattern emerging where sometimes events are detected by devices and sometimes not, and it's different between the two devices. And you'll see that in the middle there, for a couple of the devices, the Aware and the Purple Air, we don't have any data. And this is one of the challenges of using devices that are internet connected, is that sometimes if they don't have internal storage that you can access later, without an internet connection, they don't store the data. And this might be a bit tricky if we're trying to use these as control devices, because we do become internet dependent. I will say, though, that these devices do automatically detect when they have internet access again and turn themselves back on, if you will, and automatically start logging. But if we're going to be dependent on an internet connection, that's something to be thinking about if we're considering the reliability of these devices for control purposes. And the last slide here on in-home test was just a couple of cooktop events, making quesadilla and frying some eggs. And you can see a similar pattern to before, where some of the devices like the Purple Air and the Air Visual Node are pretty good at detecting these cooking events. And the Aware and the Spec, not so much. Now, we aren't the only people to be doing this sort of work. The EPA in the US has done a lot of work focusing on, can we use lower cost devices for outdoor particle sensing. The South Coast Air Quality Management District is working on outdoor testing and also doing something similar to what we did, where they're testing these devices side by side in a chamber. Carnegie Mellon University is also doing some work. They developed the spec, and they've also done some side-by-side testing. And there's also some work being done on air quality in China, and you can follow these links to get a little bit more information. But the main point here is, if we look at the test results from these other studies, they've basically found the same results that we did in terms of which sensors do best, which sensors do poorly, and also the same sort of response to different sized particle events and how these things work. And the key thing here, that one of the key reasons why there's such a difference, even though they have the same sensor in them, boils down to how the devices are calibrated and how the electronics built into them are interpreting the output of the sensor. So to sort of summarize all these test results, are these monitors or sensors good enough for doing something for ventilation control or maybe turning on a filtration system? And I think the answer is probably yes for a couple of these. The Purple Air and the Foobot, they detected almost all the sources except for a few. The ones they didn't detect were ones with the very small particles only. And they had enough of a magnitude response that you could effectively use them for control purposes. There are a few in the middle where, maybe they weren't quite as good as those first two, but they did detect most sources, but not all of them. And a couple of these devices really did not detect the particles we're interested in, either because they were calibrated in such a way they only detected large particles, or or something else in the way the electronics are interpreting the sensor output meant that they didn't detect enough of the events to be reliable, or the magnitude that they reported was so low or so variable that they weren't really reliable enough to be used for control. And one of the conclusions, I think, of some of this work is that we really need to come up with some sort of standardized test procedure for comparing devices. If we're going to use these things to control our ventilation systems, we need to know that they're going to reliably detect most things, have a reasonable estimate of the magnitude. Currently, we don't have that, but there is some work going on here in the US with one of the Building America teams trying to develop a test method that we could use. And the last thing here is that we tested these things and they were all brand new, out of the box, and we don't know how well they're going to work a few years down the road. There's certainly a possibility of things building up inside the sensors themselves, electronic drift of components and so on, that may change some of these results. And that's something that we really need to look at in the future, is possibly doing some accelerated testing or keeping these sensors activated and redo these tests in a couple of years. A few points on connectivity here. I did mention that with some of these devices, if you lose your internet connection, you lose the data. But they all differ in how they store data either in the cloud or you have access to them. And if we're going to reliably use these things as controls, we need to always confirm that the data got uploaded, maybe using some third-party software or something, because it is possible to lose your data. It could be overwritten or lost, or it simply doesn't get recorded at all. Almost all of these devices have an app for data viewing, even if they don't have a display themselves, which can be useful because it means that if there's an app that can view the data, then you could have some software that would access that data via the internet and use it for control purposes. And a couple of these devices, the Foobot and the Aware, they're all set up for something called if this then that, which are protocols for communicating with other devices. So they're a fair way down the path of having the capability built in that they would have a control signal that you could detect for turning on and off ventilation or filtration systems. For the other devices, so long as you can have something that will actually read the data in the cloud, you could write some sort of custom application that would allow you access to the data for real-time control. And the last couple of slides I have here are a bit of an offshoot from this. These are all commercially available devices I've been talking about that package basically the same sensor inside with a power supply and display, internet connectivity and everything. Something you might want to try is building your own monitor. It's relatively easy to purchase the actual particle sensors, and there's a couple of open source platforms that have been developed that have instructions and parts lists and so on, where you could have a go at building your own device. Of course, they're much cruder, they don't come in a nice package and so on, but if you want to experiment yourselves and get involved in some citizen science, you could certainly do this. And this is, I think, indicating that in the future, we might see even lower cost devices where it's simply dedicated to providing a control signal and doesn't come with complex displays and so on that would make the cost higher. And so there's the possibility to make these things a lot cheaper. There's also some prepackaged DIY and maker offerings that are sensor with the parts kit, and they're all using the same sensor as these monitors we talked about. The Environmental Protection Agency here in the US actually has a kit for schools, which is used for educational purposes, and these kits are not a lot more than the sensors. They're in the range of $50 to €50, some a little more, some a little less, depending on the complexity of the box they're in and the display that you get. But clearly there's a strong possibility here of having even lower cost things if we're just going to focus on the control.